Hello, my name is Haizhou Liu. Today, I'm very happy to talk about research that I have been doing in the past 1 year. It's about the oxidation of organic contaminants by activation of persulfate and hydrogen peroxide. Collaborators of this project, including Amanda Ackman, Anne Fine from my research group, and also my supervisor David Sitlak from Civil and Environmental Engineering, as well as Fiona Doyle from Material Science and Engineering, as well as Dibaka Bachakiita from University of Kentucky. So, as we know that the Superfund sites has a lot of different type of contaminants that are very persistent and hard to remove. They spread out in a large area in the subsurface, in the soil and groundwater. And examples of these groups of contaminants include trichloroethane, benzene, dioxin, and other halogenated aromatic compounds. The treatment technology have been developed through the past several decades, including biological remediation method, where you use microbes to eat up this type of contaminants. There is also a rather big group of treatment technology called in situ chemical oxidation, ISCO in short. This method utilizes different type of highly oxidative reagent to oxidize these contaminants. So how does in situ chemical oxidation work? So basically, we have a big plume of contaminants in the subground in this slide shown in this orange color. And then when we are going to treat the organic contaminants, we would have a truck loading with reagent. Then we inject this type of reagent into the subsurface. And then these reagents react with the reactive phases of the soil minerals to generate highly oxidative oxidants. So the oxidants permeates into the subsurface and then oxidize the contaminants. Basically, the traditional used oxidants for this in situ remediation include hydrogen peroxide. So if we look at the chemical structure of hydrogen peroxide, it has a peroxy bond. And it is because of this peroxy bond that is responsible for the highly oxidative properties of this chemical. In addition to hydrogen peroxide, a very similar compound is called persulfate. Basically, persulfate shares very similar chemical structure with hydrogen peroxide. It still has the peroxy bond, but instead of a hydrogen bonded with an oxygen, it is a SO3 group bonded with an oxygen. So how does the sulfate radical formation proceed via the persulfate activation? In the subgrounds, we have many different types of soil particles enriched in iron elements. Basically, they are iron oxide or in +3 oxidation state. So when we start to inject persulfate into the underground, persulfate oxidize react with iron 3 through an 1 electron transfer process as a redox chemical reaction. So persulfate is oxidized into persulfate radical, and in turn, iron 3 is reduced to iron 2 in the soil particles. But this is just half of the reaction. And persulfate then reacts with the reduced form of iron, which is iron 2, and oxidize iron 2 to iron 3. And the persulfate itself is activated into a sulfate anion, and more importantly, a sulfate radical. So sulfate radical is a very oxidative radical species that can be used to oxidize those contaminants in the Superfund sites. And because this is the redox cycle between iron 3 and iron 2, it activates the persulfate into sulfate radicals. So it is a catalytic reaction process controlled by the iron minerals in the subsurface. Similarly, when we inject hydrogen peroxide, It is the same catalytical reaction that produces hydroxyl radicals from hydrogen peroxide. So hydrogen peroxide reacts with iron 2 to form hydroxyl radicals. And then hydroxyl radical react with contaminants and oxidize them into less toxic forms. However, besides this main catalytical process to generate hydroxyl radicals, there are also other scavenging effects, scavenging reactions that reduce the efficiency of the generation of these highly oxidative radicals. Some of this process include, first, hydrogen peroxide can react with iron 2 through a 2-electron transfer process, and instead of producing hydroxyl radical, it produces just water molecule without any oxidative species generated. And hydroxyl radical can also react further with hydrogen peroxide to scavenge the hydroxyl radical. And there are also some other scavenging reactions that we haven't yet quantified, including the effects of organics on the generation of this type of radical. And because we know that the soil particle has different type of clay materials, which is rich in silica, and silica can interact with the surface of iron oxide, which in turn impacts the generation of hydroxyl radicals. And for sulfate radical generation through persulfate, there are also different scavenging effects, including the direct reaction of sulfate radical with persulfate, as well as other scavenging reactions to be quantified. So the main question in the activation of persulfate to sulfate radical is, how can we quantify the efficiency of sulfate radical generation? And what is the rate of activation? How fast the oxidant is generated? So based on these questions, my research goals include, first, I try to understand the efficiency of both sulfate radical and hydroxyl radical yields or generation in persulfate and hydrogen peroxide system respectively. And secondly, I want to quantify the rates of the radical activation in both the persulfate and hydrogen peroxide systems. And based on the understanding of these fundamental questions, then we will be able to predict the performance of injecting persulfate or hydrogen peroxide in the real in situ chemical oxidation treatment to see how effectively it can remove the contaminants in the subsurface. So in order to look into the fundamental mechanisms of the persulfate activation, we use model iron oxide compounds and mixing with persulfate, so it generates sulfate radicals. And then we use benzene as our target compound. It is also because benzene is a well-known toxic chemical that can cause cancer problems. And when sulfate radical reacting with benzene, it oxidizes benzene through a 1-electron transfer process and oxidizes benzene to phenol. And then if we let the system keep going, then sulfate radical can further reacting with benzene with phenol to produce a series of more hydrolyzed compounds such as catechol, hydroquinone. And then these secondary, more hydrolyzed compounds can further react with sulfate radical or direct with persulfate. And then eventually the aromatic ring is broken and produced, and then a series of small organic compounds, less toxic compounds, are formed. So in our system, have equal concentration of persulfate and benzene, and we look into the reactions in the initial phase so that phenol is accumulated through the system. And then we measure the formation of phenol, accumulation of phenol through time. And this will be able to tell us the formation and the efficiency of sulfate radical generation. So let's look at the figure on the right side. The gray triangle curve shows the stability of persulfate in the control experiment without iron oxide. But when we have iron oxide and benzene mixed into the system, then persulfate is activated into sulfate radical, and sulfate radical reacts with benzene. So we can see that through a period of 30 days, sulfate gradually decreased because that it is activated by iron minerals to generate sulfate radicals. And then if we look at the accumulation of phenol, which is the product of oxidizing benzene, we can see that through a period of 30 days, it accumulated very fast, reaching about 60 micromole after 30 days. And we define the efficiency of sulfate radical yield as the amount of phenol accumulated divided by the amount of persulfate decreased. So we can see that those square green dots shown in the figure on the right side indicate that the efficiency of sulfate radical generation is constant at about 40%. And then what about the hydrogen peroxide activation to generate hydroxyl radicals? Similarly, we use the iron oxide to activate hydrogen peroxide to form hydroxyl radicals. And then we use, instead of using benzene, we use phenol as the target compound and measure the loss of phenol through time. And the efficiency is also defined as the amount of phenol reacted divided by the amount of hydrogen peroxide reacted. And in the figure on the right side, the red curve shows the concentration of phenol decreased through time. And the blue curve shows the concentration of hydrogen peroxide decreased through time. And compare with the persulfate activation system in the last slide, we can see that the activation of hydrogen peroxide is a very fast process. Almost all the 20 millimole of hydrogen peroxide has been consumed over just 2 days instead of 30 days. And when we plot the efficiency of hydrogen peroxide activation and sulfate radical activation system together, we can see that the figure on the left block shows the results from the hydrogen peroxide activation system. We can see that the green bars indicate the efficiency of the system. We can see that for hydrogen peroxide activation, the efficiency is very small. It's less than 1% for both using amorphous iron oxide or crystallized iron oxide. And the red bars shows the half-life time of the hydrogen peroxide or persulfate. So the higher the half-life time, the slower it decays. But for hydrogen peroxide, we can see that the half-life time is less than 1 day. It's just a couple of hours. And then this indicates that for hydrogen peroxide activation system, hydrogen peroxide reacts very fast with iron oxide. But only a small amount, less than 1% of hydrogen peroxide is converted into hydroxyl radicals that is effective to remove the organic contaminants. But in contrast, the figure on the right side shows the results from the persulfate activation system. We can see that the green bars indicate that for both the amorphous iron oxide and the crystallized iron oxides, the efficiency are between 10% to 40%, and their half-life time is between 60 to 100 days. So this indicates that for persulfate activation system, it's a much slower process compared with hydrogen peroxide. but the efficiency or the converting or the transformation of persulfate into sulfate radical is at a much higher rate compared with hydrogen peroxide. So in summary, our results shows that both the persulfate iron oxide and the hydrogen peroxide iron oxide system activates the formation of highly oxidative radicals. One system, hydrogen peroxide, generates hydroxyl radicals, and persulfate generates sulfate radicals. But their efficiencies are very different. Sulfate radical yield is about 20 to 100 times higher than hydrogen peroxide system. And the rate of the persulfate loss is only about 2% of the hydrogen peroxide loss. So these have very profound implications for in situ chemical treatment. So if we think about, we have a big contaminant plume deep underground, and then when we use hydrogen peroxide as our in situ chemical oxidation reagent, when we inject hydrogen peroxide underground, it reacts very fast with the iron minerals to dispatch. And then only a small amount, less than 1% of hydrogen peroxide is activated into hydroxyl radicals. And then they react just in the subsurface. We're very close to the injection site. And so if we want to permeate the hydroxyl radicals deep underground, we need a lot of we need a lot of hydrogen peroxide, and to produce a lot of hydroxyl radicals. In contrast, when we use persulfate as our activation method, because when persulfate is activated by iron oxide, it reacts much slower, so it can permeate deeper underground and reach the contaminant plume at a much deeper distance. And then the sulfate radical can react with it. And in terms of the future plans, we are very interested in looking into other chemical parameters that impact the generation of sulfate radicals, including what's the impact of the humic substance in the soil and the impact of groundwater constituents, including, for example, carbonate concentration, chloride concentration. And I believe that when we look deep into this fundamental mechanism controlling the activation of persulfate, it can give us more confidence to increase the efficiency of this treatment, and also to control the treatability of using sulfate radical or persulfate to remove organic contaminants. So a lot of the current applications which are using hydrogen peroxide have just load hydrogen peroxide into the subsurface and then just watch the contaminants disappear without understanding the fundamental mechanism of activation. So I believe that by looking into the fundamental mechanisms of persulfate activation, we will also be able to better predict the treatment efficiency in the future. Finally, I would like to acknowledge the Superfund research program for the funding of this research program, and then the support from the Superfund research centers at both University of California, Berkeley, and University of Kentucky. Thank you.